This is Shelby Kimmel, and today I'm going to be talking about some joint work with Chung and Noel Anderson on leveraging unknown structure in quantum query algorithms. And in particular, I'm going to be talking about is leveraging unknown structure in the input to a quantum algorithm in order to get a speed up. To see an example of this, we can consider the problem of path detection. So in path detection, you're given a maze with some entrance point and some exit point. So it's just a yes/no question. Yes, there is a path, or no, there's no path. And now the example on the left has much less structure to it. There's lots of turnings and branching. However, the one on the right has a lot more structure to it. It just has this one short and simple path from the entrance to the exit. So even though these two mazes are about the same size, we would expect that for any algorithm, be it quantum or classical, it could use the structure of this easier input to more quickly determine that, yes, there is a path from the entrance to the exit, whereas kind of the unstructured, almost random looking properties of the graph on the left would make it a more harder instance to deal with. Okay, so while you would expect that a quantum algorithm could determine that there's a path faster on the easier instance, prior to our work for a large class of quantum algorithm, no matter what the instance was, whether it was easy or hard, it always used the worst case runtime. This class of algorithms was not able to take advantage of structure to get a speed up. So our result is basically to modify this very general class of algorithms in such a way that when we have those hard kind of unstructured instances, those worst case instances, our algorithm will do approximately the same as the original algorithm. But now, if we end up with an easier instance, one of those instances with structure, we can run our algorithm for a shorter amount of time and still be successful. Okay, so I'm going to introduce that large and important class of algorithms that I mentioned. Those are span program algorithms. And I'll try to give you a sense for why it's hard to speed up those easy instances. And then I will discuss an algorithm that works faster on those easier inputs. I'll talk briefly about how we extend our results to a more general problem called state generation. And I'll close with some applications and future work. Okay, so span program algorithms are an important quantum algorithm design paradigm. It's a method that can be used to design quantum query algorithms to evaluate a binary function. So f is a yes/no function, a binary function, and it evaluates it on an input x prime, and it should be able to do that for any x prime in some set or domain x. In the setup of this kind of query algorithm, you know ahead of time what big X is, so you know that set of all possible inputs to your function that you might get. And then your goal is to create an algorithm so that if you're given a specific input, a specific instance, x prime, then you want to evaluate whether f is yes or no on that input. And this is a quantum query algorithm. You're given information about that instance through an oracle, O sub x prime, and that oracle is a unitary operation. And what that unitary operation gives you is basically with one use of that unitary, you can learn about one bit of the input. And with a quantum query algorithm, the figure of merit, the thing that we're trying to minimize, is the number of uses of this unitary oracle O sub x prime. And every time we use the oracle, we call it a query. So another way of thinking about this is we'd like to determine whether the value of f is yes or no on a certain input, but we'd like to do it while learning as little about the input as possible, because every time we use the oracle, we learn a little bit more about that input, but we basically want to minimize those uses. And in this model, all other operations are free. The number of queries, we also call that the query complexity. And throughout the talk, I'll sometimes refer to runtime just because it's kind of a more natural way to phrase things. But whenever I'm talking about runtime, really what I'm talking about in this talk is query complexity. So if I say something like we're going to try and speed up the algorithm, really what that means is we're going to try to create an algorithm that uses fewer queries. Okay, and so this span program algorithm paradigm or method for designing algorithms, what makes it so useful and so powerful is that there is always, using this paradigm, you can always create an optimal query algorithm. And what we mean by optimal is that if you look at how the algorithm performs over all possible inputs, over all of the domain X, the algorithm will use as few queries as possible in the worst case. And so because of this, because you can always create an optimal span program algorithm, this paradigm is very powerful, it's very general, and so instead of kind of thinking about all the possible ways that we could possibly design quantum query algorithms, if we just restrict to span program algorithms, we don't actually lose generality in our approach. Okay, so while these span programs are very powerful, in the standard kind of query model, the thing that you're trying to optimize is in the worst case over all possible inputs. And so what hadn't been kind of known previously or studied previously was, well, what about those easier, not worst case inputs that you might get? What if you want to get a speed up on those easier instances? Previous work in this area had said, well, what if you were given a promise ahead of time that you're not necessarily going to be given an instance from that full set X, but rather from a smaller subset E, where E only contains some easier instances. And this was an interesting question because given a span program algorithm, you could ask, well, what is that set E that the algorithm should run faster on? And what kind of structure did those instances have? And what we do is we remove that promise. So the instance is coming from the full set X, and it could be one of those hard worst case instances, or it could be from this kind of easier set E. We don't know that ahead of time, but if it is from this set that kind of people have in prior work have found should be easier, we show that then in that case you can get a speed up. But all prior work in this area had this promise. I'm going to try to explain why it was challenging in prior work to remove this promise. And to explain that, I need to remind you about phase estimation. Okay, so phase estimation is kind of the key subroutine that's used in span program algorithms. And in phase estimation, what you're given is a unitary U and a state psi, which without loss of generality, we can just write as a superposition of eigenvectors of U. And now because U is a unitary, all of the eigenvalues of its eigenvectors have the form e to the 2 pi I times some lambda. And we call that lambda the phase or the eigenphase of the corresponding eigenvector. And also you're given a precision parameter theta. Okay, so given all these things as part of your input, the output of phase estimation is with some probability that scales like the amplitude squared of an eigenvector in the state psi. You get an approximation of the absolute value of the phase, the eigenphase of that corresponding eigenvector. And the approximation is good to some precision that scales like 1 over theta. When you're designing a span program algorithm to evaluate a function f on some domain x, what this kind of paradigm helps you to do is it allows you to design a unitary U. The unitary U involves the oracle that gives you the description of the input. It also prescribes how to create an input state psi, and it prescribes a specific precision parameter theta, such that when you run phase estimation on this particular U, psi, and theta, for every possible instance in the domain, if it's a yes instance, so if f of x prime equals yes, then when you run phase estimation, you're going to get an output phase of 0 with high probability. And if you have a no instance, the output phase is not 0 with high probability. So that's what the standard span program algorithm does. But what we're interested in doing is, well, what if you don't have a worst case input? What if you have an input with some structure that you expect should be easier for your quantum algorithm? Shouldn't you be able to run this algorithm for less time using fewer queries and still get a good result? And so there's in phase estimation, there's one kind of critical knob that we can turn that changes the runtime, that changes the number of queries. And that is this parameter theta. So the larger you make theta, which means like the more accurate your estimate is of the phase, the longer your runtime is, the more queries the algorithm needs. So it seems like an obvious first approach would just be, well, let's just try running this algorithm with a smaller theta, which will give us worse precision, but hopefully if we have an easier input, we should just be able to get a good answer. And that would give us an algorithm that gives us a speed up for these easier instances with structure. But it turns out that if you just try to do this kind of in the naive way, you get stuck. And I'm going to try to explain why that is the case. Okay, so we're kind of examining this question of what happens when we reduce the precision, when we reduce this parameter theta. Before we reduce it, let's just kind of think about what happens before we reduce it, when we just use the standard large value of theta. And in particular, let's think about what happens when we have one of these kind of worst case, very hard no instances. So a no instance, we want the output phase to not be 0 with high probability. But what we can show is that for those hard no instances, you tend to have, if we look at the eigenphase of the input state psi, you tend to have superpositions of states with very low phases that are very close to 0. So this is kind of graphically trying to represent that we have a low-lying phase for our state psi. We want to look at what happens when we do phase estimation. So this graph, or this kind of figure over here, is representing the outcome probability of phase estimation when we have this initial state. So if you see, so I've drawn these tick marks at intervals of multiples of 1 over theta. And you can see that this phase is kind of sitting somewhere between 1 over theta and 2 over theta. And so what phase estimation does is it can only output multiples of 1 over theta. And it basically snaps to one of those multiples of 1 over theta that is closest to the actual value of lambda. And so what we see is that because the kind of closest values of 1 over theta to our value of lambda are 1 over theta and 2 over theta, we have very low probability of getting an outcome of 0, which is what we wanted. Remember, no instances, we wanted a low outcome of probability 0. Where here the length of these arrows is kind of meant to describe the probability of getting that outcome. So as I said, this is kind of a picture of what happens when we actually don't reduce the precision, when we have a large precision that is prescribed by the kind of standard algorithm. And so we want to consider what happens when we just reduce that precision, because we're hoping that we can reduce that precision, and then if we have an easy input, then we'll be able to do better. But the problem is that if we still consider a hard instance, so when we have a hard instance, again, we have an eigenphase that is kind of low-lying, it's close to 0. And now when we've reduced our precision, we now have a theta prime that is smaller than our original theta. What that does is it spaces out these tick marks. When we run phase estimation, we have a high probability of ending up at either position 1 over theta prime or 0. And so this means that we're going to get an outcome of 0 when we run phase estimation with high probability. And so this is bad because we said that when we get an outcome of phase 0, we're going to interpret that as a yes instance. And since we don't know ahead of time whether we have an easy instance or a hard instance, this is kind of where the trouble lies. If we get a phase 0 with low precision, it might be a false yes, it might be a true yes, it might be a hard no. We really can't tell the difference. Okay, and kind of the root of this problem is that the standard span program algorithm for evaluating functions just has 2 outputs, yes or no. And that's not really sufficient for us because we don't know for those yes and no's, are those true yeses or no's, or are they kind of false positives, false negatives? Really what we would love to have is an algorithm that has 3 outputs, a definite yes, a definite no, or a flag that you have insufficient queries and you need to kind of rerun the algorithm and use more queries or longer runtime. Okay, so hopefully that gave you a little sense as to why kind of the naive approach to trying to speed up the span program algorithm won't work. But I will now talk about our solution. We're actually just going to take the same approach. We are going to just try to reduce that precision because that's going to give us an algorithm with fewer queries, but we're just going to be a little bit more careful about how we do it. And so in particular, what we're going to look at first are yes instances. So remember, for yes instances over here, we want a high probability of outcome 0 when we run phase estimation. And what we do is we tweaked a couple of other knobs in our algorithm so that no matter what the precision is, whether theta is a large value or a small value, for any precision, if we have a yes instance, we're always going to have a high probability of outcome 0. what that looks like is something like this. So we might have the state, our input state psi might be a superposition of several eigenvectors with several eigenphases, but there's going to be large amplitude on at least one eigenvector with phase that is 0. And so then when we go to measure the outcome probabilities, we're going to have high probability of getting a 0 phase outcome. And then the second thing that we notice is that, okay, well, we saw that when we reduced the precisions with a hard no instance, we were in trouble. But let's think about what happens when we reduce the precision with an easy no instance. So now what we are able to show is that for those easy no instances, if you look at the eigenphases of the input state psi, they're kind of gapped away from 0. And so now when you reduce the precision, and so we're kind of spreading out these tick marks, and so now when we go to measure the outcome of phase estimation, we're going to get values like 2 over theta prime or 1 over theta prime for this easier no instance. And this is good because we wanted for no instances that there is a low probability of outcome 0, and that's what we get in this case for the easy no instance. But now we're getting somewhere because we've adjusted things so that if it's a yes instance, it always definitely gets that outcome of phase 0, no matter the precision. So we know yes instances always get 0 outcomes. So if we see a non-zero outcome, like this 1 over theta prime, even with low precision, we know for sure that it's a no instance. It can't be a yes instance. So even though what we kind of wanted, maybe ideally, was an algorithm that output yes, no, or a third option being kind of insufficient queries, you need to rerun with longer runtime and more queries. What our kind of modified algorithm does is as follows. It just still has 2 outputs. And what those outputs are that you have a definite no outcome, and then you have a second outcome which is ambiguous. It's kind of, well, maybe it's yes, or maybe it's insufficient queries, and that means you need to kind of rerun and try to run your algorithm with more queries, longer runtime. Okay, so this leads to I can kind of describe our approach now. What we do is we run the span program phase estimation algorithm, and we do it kind of iteratively with exponentially increasing precision theta. So we kind of first run for runtime 2, then 4, then 8, then 16, and so on. And we do that until we reach the precision of the original algorithm. And at each iteration, we run the phase estimation algorithm. And if we get a 0 phase at any repetition, this was what I just said was our ambiguous outcome, where we don't know if it's a true yes or a false yes. So if that happens, we just continue with in the next round with increased precision. But if at any iteration we get a non-zero phase, in that case, we're confident that we have a no, and so we can just stop the whole algorithm, break out of this loop, and output no. And what we prove is that this results in a faster runtime for easy no instances. Okay, but you might be wondering about what about easy yes instances? So what we do is we design a negation procedure that produces a span program algorithm for kind of the negation of the original function. So every instance that was a yes in the original function, it becomes a no, and vice versa. But in particular, what this negation preserves is the difficulty of the instance. So formerly easy yes instances now become easy no instances. We're not the first to kind of design a negation procedure for span programs, although we use a more general span program algorithm than was used previously for these negation procedures. So we kind of had to modify this negation to work in our case. Okay, so putting it all together, our algorithm is the following. We iterate with kind of a loop with exponentially increasing precision. And at each iteration, we run 2 algorithms. We run our original span program algorithm, and we run our negated span program algorithm. And for the original algorithm, if we get a non-zero phase at any repetition, we stop and output no. And for the negated span program algorithm, if we get a non-zero phase at any repetition, we stop and output yes, because now in the negated version, those no instances actually correspond to yeses. And so putting this all together, we get an algorithm that runs faster for easy yes and no instances. And in the case when we have a hard instance where we keep getting those ambiguous out, we just keep going. But because we have this geometric scaling of our iterations, the total runtime is approximately the same as it would have been if we had just gone straight to the maximum precision and run at that point. And we do incur kind of log factors as overhead to reduce the error, but essentially we end up with the same runtime as before, as the original span program algorithm. And I'll just mention that, I would say this is like morally what is going on with our algorithm. The details, if you look at our paper, are a bit different. We actually, the unambiguous outcome is actually the yes instances when we kind of analyze things instead of the no instances. And there's some other details and knobs that we have to turn, but hopefully this will kind of give you the big picture idea so that if you do go and look at our paper, you'll have a sense for why we're doing what we're doing. Okay, so just to describe a little bit more about how our algorithm actually does in practice, and to get back to this bigger question of what do we mean by structure. So to kind of bring all that together, I'll tell you that for a span program algorithm, each instance in the domain big X has a witness size, Wx. And that witness size is essentially a measure of how difficult that instance is. And it's often a measure of some type of structure in the instance. Okay, so with the original span program algorithm, the query complexity scales like the following. So it's the square root of two terms. And what's important to notice is that both of those terms have a max in them. So we're taking the term on the left is we take the maximum witness size over all yes instances. The term on the right, we take the maximum witness size over all no instances. And so here you can literally see why we're getting that kind of worst case query complexity. Like this query complexity doesn't at all depend on the specific instance that you're working with. It only depends on the worst case. So with our kind of modified algorithm, in this first case, if the input instance x prime is a yes instance, then instead of having this term where we took the maximum over all yes instances, that's replaced by just the witness size of the particular instance that we have. And so in the case that we happen to have a worst case input where the witness size is that equal to that maximum, then these two expressions inside the big O are exactly the same. And so we're recovering kind of the original query complexity of the original algorithm, except there's this little tilde on the O, which is hiding some log factors. But of course, if this witness size of our particular input is smaller than the max, then we will get an improvement over the original span program. And we have a similar runtime for no, except that we replace this maximum over all no instances with the particular witness size of the particular no instance that we have. Okay, so that was our approach, and I'll close with a brief discussion of state generation, some applications, and future work. Okay, so state generation is a more general problem where instead of just trying to evaluate a function, what you're trying to do is create a quantum state. So you're given as input a state rho x, and your goal is to create from that state a new state sigma x. And you're given access, just as before, this is a query problem, you're given access to an oracle OX that encodes some instance X, and depending on what that instance X is, that determines what your final output state is, and it also kind of corresponds to your input state. This is, you can kind of use this to encode the function evaluation problem, but you can also use it to encode a much more general kind of class of problems. But it turns out that there is, similarly to function evaluation, there's a nearly optimal span program-like algorithm, but that's optimal in the worst case for those kind of worst case hardest inputs. And what previously wasn't known was how to improve this algorithm if you have easier inputs. And one of the main challenges to kind of extending our ideas to the state generation problem is that the original algorithm doesn't have any measurements. You just apply a unitary to your original state, and that unitary involves applying the oracle unitary many times. And then at the end of the day, you're left with your output state. But there's, we need to have a measurement that tells us like, oh, you have your algorithm has run for long enough, you can stop, or maybe it's ambiguous and you need to run for longer to be sure that you've run for long enough. But there's no measurement like that we could kind of use as a starting point in the original algorithm. So what we had to do was design a kind of separate new test that is kind of a new addition to the algorithm that does something similar to what we've seen with our span program algorithm approach. It's kind of a test that has this one-sided error nature to it, where it's like if you get one outcome, you know you're going to be running for long enough. If you get the other outcome, it's kind of ambiguous and you need to rerun with more queries. But using that test, we can kind of get a similar result for this more general problem. Okay, and so to applications and future work, we have seen that the query complexity is related to these witness size. And there's been a lot of prior work trying to understand how witness sizes relate to the structure in the instance because of the work that people have done on the promise version of this problem, where people were interested, well, if we can promise that we only have instances with small witness size, that will give us a faster algorithm. So for example, with the problem of cycle detection, where you're trying to detect a cycle in a graph, for example, in the yes case, the witness size is equal to 1 over the cycle rank, where cycle rank is a measure of essentially the number of cycles in the graph. And so this kind of makes sense. Like if you have a lot of cycles, that means that the witness size is going to be small, which means that you're going to get a speed up. It kind of makes sense that if there's a structure with a lot of cycles, a quantum algorithm should be able to take advantage of that to get a faster runtime. Prior to our work, it wasn't really known how to do that unless you were promised ahead of time that you had an instance with a large cycle rank. And so you can see there's kind of similar like structures and correspondences for other types of problems here. And this is all kind of prior work that people have done to understand these correspondences, but we can immediately leverage this understanding to understand how span program algorithms will get sped up even if you don't have a promise. Okay, and I'll close by mentioning some future work. I mentioned that we have our algorithm is almost as good as the prior kind of original span program algorithm, except for these log factors. And it would be kind of great to just remove those and have our algorithm just work as well as the original in the worst case. And we're interested in applying fixed point methods to do this, which have been successful in removing those log factors for the search problem, which Chung, Low, and Yoder worked on that. Our work also gives opportunities to study average case quantum versus classical speedups, improvements in query complexity. Before, if the quantum algorithms always just use the worst case query complexity, you couldn't even analyze average case. But now we could consider, well, what if you have a certain distribution over inputs? How well would the quantum algorithm do on average versus a classical algorithm? It turns out that for the state generation extension that I mentioned, the error parameters scaling is pretty terrible, so we would love to improve that. And finally, all of our work applies to these very specific paradigms, kind of based on these span program type algorithms, but that's just one way that you can design quantum query algorithms. So it would be interesting if we could use these ideas to speed up other types of algorithms, maybe that are also based on phase estimation. So with that, I want to thank you for listening. Thanks to my funding sources, and thanks to my collaborators, Noel and Jayu, and I hope you'll check out our paper when you have a chance. The archive number is at the top.